Good morning, good afternoon, or good evening. I'm Sahil Garg, and I'm very excited to be presenting our work on extracting structured information from unstructured text. I would like to mention that although I'm presenting this work today, this is a joint work with Ajinkya, Sriram, Chiranjib, and Deepak. In this work, we propose a framework and a model so as to extract entities from a set of documents and using very few initial annotations given and extract a large set of entities from multiple documents in a corpus. So in the next 20 minutes or so, I will take you through the motivation of this work and then the design and implementation that we followed by the results that we got and some of the observations that we made. And finally, I will talk about some of the future work that can be done. So to start off, the motivation and application areas for this particular work is particularly entailing to chatbots, which is a technology that is currently in heavy demand. And according to industry research, chatbots are predicted to almost solve 90% of customer inquiries in the next 5 years. And this means that a lot of solutions that are given by on-call engineers today will have been moved to chatbots. And for chatbots to do this task of finding solutions and helping customers, there needs to be certain information that needs to be provided to these chatbots, and certain entities need to be taken from the answers of on-call engineers and different resources and so on. So to do this, the chatbots heavily rely on using NER, which is named entity recognition, and closed domain question answering. So named entity recognition is a way where given a document, it tries to find words and assigns them to a set of tags, such as a person, a location, or an organization. And these tags are helpful to identify these pieces of information and use them in another context. So to perform this task of named entity recognition, there are several large data sets that exist. Some of the famous ones being ConNL data set, which is about 200,000 tokens, and it associates these tokens with tags such as person and location and so on. Another one is onto nodes, where it takes about 1.7 million tokens and then attributes them to tags for numbers, quantity, person, location, and many more such tags. So the fact is that these data sets allow you to perform and find entities for certain particular tags, but it is not easy to develop these NERs for custom entities and to extract any entity that you want from a particular data set or a corpus of documents. So in our project, we aim to extract any custom entity that has some kind of structure in the entity value itself from a set of documents that can be natural language text. And to do this, we follow the following design that you see on the screen right now. We basically iterate between an ML model and a program synthesizer, and each one trying to improve the performance of the other, so as to extract more and more entities from a set of documents and improve the quality of those entities so as to get the right values that we are looking for. So initially, the input to the system is the entity we are looking for, as well as a small set of human annotated inputs. This is sent to an ML model along with the corpus of all the documents that we have, and the ML model generates a set of outputs which are entities extracted on some of these documents using the examples of the annotated inputs. And these outputs are usually noisy in nature. They're not always correct. So these are sent to the program synthesizer module, which tries to learn a program for these particular outputs generated by the ML model. So to do this, it also takes in a set of regular expressions, and these regular expressions are trained using the text matching API of Prose, which uses the noisy annotations and the outputs of the ML model to learn certain regular expressions and figure out the structure in these values. And these regular expressions, along with the outputs, are used in the program synthesizer module. Another thing that the program synthesizer uses is subject identification. This is to use the context of the article, a blog, natural language text document itself. And for example, when we are trying to extract the screen size from a set of documents that are pertaining to reviews of phones, the subject is the primary phone that the review is about. And how we perform this subject identification is by using a regular expression that can match names of the products and find the product that occurs the maximum number of times in that document. And we assume that this is the product that is the main phone or the item that's being the subject of the article. And so the actual entity that we try to extract should be closer to this subject. The benefit of this is when there are two such entities that follow these regular expressions and match them. For example, in an article where there are two phones being compared and there is the screen size of both of them mentioned in the article, both of these are correct screen sizes. But when we want to extract the one for the subject of the article, we assume that it's closer to the name of the subject itself. And so we, using subject identification, we search for this entity only in a small window around that subject name, which helps us find the correct entity corresponding to that subject. Along with the outputs of the ML model and these regular expressions and the subject, there can also be certain field constraints that can be mentioned by the user itself if there are certain specific constraints on these output values. And the program synthesizer then generates a set of these disjunctive programs using a technique of clustering, which I will talk about later, where and these programs are sent to a semi-automated annotator, which runs these programs on the rest of the documents and all the documents that exist in the corpus to generate these entities. And these are again then fed to the ML model to improve the performance of the ML model. And this is done iteratively so as to reach a point where both the ML model and the synthesizer are in harmony. So the first step is to have a small set of human annotated values. So as you see, res is in this JSON format is the custom annotation that we want to extract, and this is the screen size that we want to get from the article. So the file name is the name of the review, and the res is the screen size, which follows a pattern such as a number followed by the keyword inch, which is a unit, and also or the symbol of inch. And so that is the structure that we learn. And this technique works for all entities that have such a structure where it's followed by a particular unit or certain other constant strings. So the first step is we take these human inputs, annotations, and feed them into the ML model, which we train using the Spacey library. And the ML model generates these set of outputs for certain annotations. So it's able to find out, it's able to annotate about 30 to 50% of the files. And there's an F1 score of about 0.5. And you can see some of the values that are found using the ML model. So to improve this and to also find annotations for the rest of the documents, which is a huge chunk, we take these outputs to the program synthesizer module. And before we do that, we learn regular expressions on the outputs that were generated by the ML model. And here are some of the examples of the regular expressions that you see. So some of these are followed by -inch and or the inch symbol, and they are able to get the structure, to learn the structure of the actual entity itself and represent that. We sample the outputs of the ML model and try to learn these regular expressions, because when we try to learn it for the entire set of outputs, it also learns a lot of generic regular expressions. But when we sample and learn only for small sets and then combine them together, we're able to learn much more specific regular expressions to capture the structure. Next, we learn programs in the program synthesizer stage in the form of clusters. So whenever we take all the input-output examples from the ML model one by one, and we try to put them in one of the clusters that have been defined. And each cluster is basically a set of I/O examples with a program that's associated with that cluster. So that program is the one that matches the I/O examples in that cluster. And we try to run a new, we loop across all these I/O examples, and for each one of them, we try to see if it matches any of the previously learned programs in those clusters. If it does, we just put that I/O example into that cluster. And if it doesn't, we add that I/O example into the cluster for all these clusters itself, and then try to learn a new program on that. If there is a program that we can learn, we add this I/O example into that cluster and save that new program. And if there is no program that can be learned across all the clusters, as well as it does not match any of the cluster programs, then we create a new cluster with this I/O example and just try to learn a program for this particular example. If that is also not there, then if there is still no program that can be learned, we just add this I/O example into a list of unlearnable I/Os. Otherwise, we create a new cluster and save that. So the way we process this is we sort the clusters in the descending order by size. So we always try to match with the cluster of the highest size, and this ensures that we're trying to learn the most specific program that is associated with these values, and using that and trying to get the maximum number of I/O examples associated to that cluster. So as you see, we loop across all these I/O examples and keep adding them to clusters, and trying to add them in the order of decreasing order of size in terms of the cluster size of number of I/O examples. So here are some examples of the programs that we learn. As you see, some of these very nicely capture the essence of what we're trying to extract from the screen size. If you look at program 1 in this list, it talks about a substring in the article which has the left starting point matching regular expression space on the left and a number and the inch symbol on the right, whereas the right end matches the number on the left and space on the right. So this program would effectively extract the number and the inch symbol that exists in the article. And similarly, the program 7 again has this substring where the left end of the substring matches a space on the left and a number dash inch on the right, whereas the right end matches the number dash inch and some other symbols on the right end. So program 7 will extract these values which are the number and followed by a dash inch in the essay as a substring. So using this, we then run these programs on the entire set of documents that we have and generate new annotations. And in the first iteration, we are able to generate approximately 100 new annotations that were not found by the ML model, some of which are shown on the screen below, like for the Nokia 7.1 hands-on review.txt, we are able to extract the value 5.84-inch, which was not extracted earlier by the ML model. And we then just repeat this process and iterate between the model and the synthesizer as long as we can find new or changed entities being extracted from the documents. So we present our results in 2 data sets. The first one is 1,000 English blog articles about smartphones, and we try to extract the screen size and resolution for them. And the second one is 500 Hindi language articles, and we try to extract the price and screen size. So we pick approximately 10% of the articles from each data set, and entities are extracted from them manually to form the ground truth, and the rest of the data is considered as training data. And then we, after each iteration of the trained ML model and the synthesized disjunctive program, we run it with this test set as input, and try to calculate the precision and recall of the outputs generated by these runs. And the ground truth is not accessed during training or the synthesizing parts of the iterations. The 10% of the articles that are extracted manually form the ground truth that we want to compare our results with. So when we run it for the Hindi data set and we try to extract screen size, here are some of the programs that we learn and the performance that we get. And you can see how we learn programs such as a substring where the left end matches with a space on the left side and the number inch written in Hindi on the right. And similarly for the other end of the substring, so as to extract the string, which is the number followed by inch in Hindi. And this is independent of the language. So even with Hindi articles, we were able to extract these values well. And if you see through the iterations, you see that the precision increases from 0.78 to 0.9 as we go through the third and from the third to the fourth iteration. And the recall also increases, improving the F1 score from 0.65 to 0.76. When we try to extract the price entity from in the Hindi data set, we also observe similar results. And here are some of the programs that we see in that case. Finally, the English data set where we are trying to extract screen size, we learned 26 programs, and some of them that exist are shown here. So there are a lot of these good programs where we see the value and the symbol being or the unit being extracted appropriately, but then there are also a couple of bad programs that we see lower in the list because there are fewer such examples, and this could be because of certain fixed values being learned in the program, like 6.53 inch, and the precision and recall is again around 0.8 and 0.7. So we get an F1 score of approximately 0.7. So all of this was without using the subject identification that I spoke about when I'm talking about the design. And when we include this subject identification and we perform the search for the entity only near the particular subject, we learn these other set of programs like substring near the subject, and then followed by the relative positions. And we can see that the recall and the precision improve when we are using substring with the search near the context instead of without it. But there are also a couple of bad programs that we see, such as this one that is highlighted in green here, where the output takes a large string and it's not just the value that we want to extract, and this can add more noise. So some of the observations that we saw are that performance is sensitive to mistakes in initial human provided data, and the substring near subject helps the performance. Finally, talking about some of the future work that is possible. So giving a summary of what we have done, we currently use the tool to show promise in helping training machine learning models, and we combine synthesis with this to improve the performance. And in the future, we wish to have a theoretical analysis for increasing the performance that we see, and show guarantees on initial inputs, as well as the current evaluation is preliminary, and we want to test for the robustness of this tool by trying it out for various other entities and for various other data sets. We also want to look into if there are other ways to give context to search instead of just trying to find the subject and looking for the entity nearby it. Thank you.